Good morning, students. I welcome you to second session of mine on electrochemistry. In the first session, I discussed about the definition of electrochemistry and also what are electrolytic and galvanic cells and their differences. So with that background, today we shall move on to representation of a galvanic cell and writing a cell reaction. So today we'll be learning about how to represent a cell and how to write the cell reaction. Then also we'll be learning about what are electrode potentials, how electrode potential develops, and what are the types of electrode potentials, and what is the sign convention, and what is the sign used for mentioning electrode potential. Then we will be learning about what is standard EMF of the cell and EMF of the cell, and also we will be learning about reversible and irreversible cells. So we learned that electrochemistry is the study of interconversion of electrical energy and chemical energy. And electrical energy is converted into chemical energy in an electrolytic cell, and chemical energy is converted into electrical energy in a galvanic cell. And in both the cases, it is a redox reaction. Whether it's a galvanic cell or an electrolytic cell, the reaction taking place in these cells is a redox reaction. The only difference is, in an electrolytic cell, the redox reaction is a non-spontaneous one, and in the galvanic cell, the redox reaction that occurs is a spontaneous redox reaction. Because in the electrolytic cell, as long as the current is passed through the electrolyte, the redox reaction takes place. The moment we stop passing the current, the electrolytic decomposition or electrolysis, which is nothing but a redox reaction, stops. The moment passage of current is stopped, the redox reaction in the electrolytic cell stops. Hence it is a non-spontaneous one. Whereas in the case of galvanic cell, as long as EMF of the cell is non-zero, it's positive, so we can draw the electricity from the cell. So it is a spontaneous redox reaction. So today we shall see how to represent a galvanic cell. When I say cell, cell is always made up of a pair of electrodes. One is an anode, the other one is cathode. Whether it's an electrolytic cell or a galvanic cell, it is made up of two electrodes, an anode and a cathode. And oxidation occurs at anode, reduction occurs at cathode in electrolytic as well as galvanic cells. I repeat, oxidation occurs at anode and reduction occurs at cathode in electrolytic as well as galvanic cells. So how to represent a cell? Because a cell is constructed using two different electrodes. A galvanic cell is constructed using two different electrodes. For example, if you take Daniell cell is made up of zinc and copper electrodes. So zinc rod is dipped into zinc sulfate solution, copper rod is dipped into copper sulfate solution. Both are connected externally by a wire and internally through a salt bridge. So when we represent diagrammatically the Daniell cell, we represent like this. So this is how we diagrammatically represent Daniell cell, where we have zinc electrode dipped in zinc sulfate solution and copper electrode dipped in copper sulfate solution. And both these electrodes are connected externally by a wire. And these two wires are connected to a galvanometer, which measures the current flowing through the circuit. And this is the salt bridge. We will be learning what is salt bridge in the later classes. So salt bridge is used to complete the circuit. So this is the diagrammatic representation of Daniell cell. and it is always time consuming to represent a cell diagrammatically. Therefore, IUPAC has devised a standard method of representing a galvanic cell. So today let us see how to represent according to IUPAC convention a galvanic cell. So while representing a galvanic cell, anode is written first, followed by cathode. So according to IUPAC convention of representation of a cell, anode is written first, followed by cathode. And how to identify anode and cathode, we'll learn it a bit later. Looking at the standard reduction potentials, we can predict which is an anode and which is a cathode among the pair of electrodes given. So anode is written first, followed by cathode. And how an anode is represented? Metal followed by metal ion. And how cathode is represented? Metal ion followed by metal. So I have seen zinc rod dipped into zinc sulfate. Zinc rod is a solid material. Zinc sulfate is a solution. So the solid is in contact with the solution. So there is an interface between zinc rod and zinc sulfate solution. That interface is shown by a single line. While representing a galvanic cell, the interface between the electrode and electrolyte is represented by a single line. So also here, cathode, we have metal in contact with the metal ion solution. So the interface between the metal and the metal ion solution is represented by a single vertical line. And we have seen in the DNL cell, the zinc electrode and copper electrode are connected by a salt bridge. So salt bridge is represented by two vertical lines. This is the general representation of a galvanic cell, or standard representation of a galvanic cell. So anode is written on the left side, followed by cathode. Anode is represented as metal, followed by metal ion, and cathode is represented or written as metal ion followed by metal. Right. So in DNL cell, zinc electrode is anode and copper electrode is cathode. So now let us try to represent the DNL cell. So DNL cell is made up of zinc and copper electrodes. Zinc is anode and copper electrode is cathode. So what we write? Anode first, zinc metal in contact with Zn2 plus. You can represent concentration by C1, and there is a salt bridge which connects zinc electrode with the copper electrode. And anode, each electrode in a cell is called half cell, and this is called anode compartment. And then we have cathode compartment where we have copper ions, let us say C2 concentration, in contact with the copper electrode. So this is the way of representing a galvanic cell. This is IUPAC convention of representing a galvanic cell. Similarly, if I take zinc and silver electrodes, zinc and silver electrode, a galvanic cell made up of zinc and silver electrodes. Again here, reduction potential of reduction potential of silver being more than reduction potential of zinc, silver electrode acts as cathode and zinc electrode acts as anode. So how do we represent this cell made up of zinc and silver electrodes? Very simple. So zinc in contact with Zn2 plus ions of concentration C1, and it is connected to silver electrode to a salt bridge. Salt bridge is represented by two vertical lines, and silver ion concentration C2. This is silver. Okay. So this is how we represent a galvanic cell. So while representing a galvanic cell, anode is written first, followed by cathode. Anode is represented as metal, followed by metal ion, and cathode is written as metal ion followed by metal, and the interface between the metal and electrolyte, electrode and electrolyte, is shown by single vertical line, and the salt bridge is represented by two vertical lines. Right. Now, so after knowing what is the standard way or IUPAC convention way of representing a cell, then what is a cell reaction? How to write a cell reaction? I said oxidation takes place at zinc electrode, at anode, and reduction takes place at cathode. So in zinc copper electrode system, zinc acts as anode and copper acts as cathode. So if you consider cell reaction in a Daniell cell, at anode oxidation takes place, and anode is zinc electrode. So at anode, zinc undergoes oxidation, or I can represent this as C1 concentration as I have represented earlier. Then at cathode, reduction takes place, and the copper electrode is the cathode here. So reduction is nothing but the gaining of electrons. So copper, two ions are reduced to copper. So this is the oxidation reaction taking place at anode, that is zinc electrode, and this is the reduction reaction taking place at cathode. And oxidation is the process of losing electrons, reduction is process of gaining the electrons. This is the anode reaction, this is cathode reaction. And since a cell is made up of a pair of electrodes, each electrode is called half cell, and this is one half cell reaction, this is the other half cell reaction. And this is the reaction taking place in anode compartment, this is the reaction taking place in cathode compartment. And overall reaction is what? That zinc plus S stands for solid, giving rise to Zn2 plus C1 plus copper. This is the cell reaction. Okay, so cell reaction is nothing but the combination of oxidation and reduction processes taking place at the anode and cathode. Similarly, if we consider copper-silver electrode system, so in copper-silver electrode system, copper acts as anode, so it's written first, and silver acts as cathode, and it is written next to that. And this is the representation of a galvanic cell constructed using copper electrode and silver electrode. So what is the cell reaction? At anode, oxidation takes place. So copper undergoes oxidation, and at cathode, reduction takes place. So this is the reduction process and this is the oxidation process occurring in the cell made up of copper and silver electrodes. So the next cell reaction is the net cell reaction. So once we know what are the electrodes that constitute a galvanic cell, it is very easy to write the cell reaction. So what are electrodes I considered till now? I considered metal ion electrodes. It can be a gas electrode also, like hydrogen gas electrode, oxygen gas electrode, or chlorine gas electrode. So you should remember, there are 4 different types of electrodes, which is not part of your curriculum. For extra information, I am saying that there are 4 types of electrodes, namely metal ion electrodes, gas electrodes, metal insoluble metal ion electrodes and redox electrodes. So these are the four categories of electrodes. Right, so whatever I discussed, these are the examples of metal ion electrodes, because a metal is in contact with its own ions. Zinc in contact with Zn2 plus, silver in contact with the silver plus. So all these are metal ion electrodes. So if you consider gas electrode, hydrogen gas passed into a solution containing H plus ions like HCl. So it forms a gas electrode. Chlorine gas passed into a solution containing Cl minus ions. So it is an example of a gas electrode. Then we have for metal insoluble metal ion electrodes. So calomel electrode, which we'll be discussing in one of our future sessions. So calomel electrode, silver chloride electrodes are examples of metal insoluble metal salt ion electrodes. The last category is redox electrode. Let's not worry about that. Okay, so I've learned how to represent a galvanic cell and how to write a cell reaction. Now let us move on to electrode potential, its definition and sign convention. So whenever we place an electrode, like we place a zinc electrode into zinc sulfate solution. So whenever we place a metal rod into solution of its own ions, there will be two tendencies of the metal. What are the two tendencies of the metal? Metal can undergo oxidation, or metal ions can undergo reduction. So whenever a metal rod is dipped into a solution of its own ions, there are two processes which are competing. One is oxidation process, the other one is a reduction process. So which of these two processes occurs at a particular electrode is decided by the other electrode with which this is connected. So whenever we place a zinc rod into zinc sulfate solution, zinc tries to undergo oxidation like this, or zinc ions try to undergo reduction like this to form zinc. So both these processes will be competing with each other. Reduction and oxidation will be competing with each other to occur here. But neither of these two processes occurs as long as this electrode is not connected to another electrode. Okay, so single electrode is of no use. We cannot achieve any purpose using a single electrode. We always require a pair of electrodes to perform or achieve something. So when we have a zinc rod dipped into zinc sulfate solution, there is a tendency of the metal to go into the solution as metal ions through oxidation, and there is also a tendency of the metal ions to form the metal ion through reduction. So this tendency of the metal or electrode to lose or gain the electrons is called electrode potential. So what is electrode potential? Electrode potential is the tendency of the electrode to lose or gain the electrons. Whether the electrode loses the electrons or gains the electrons depends upon the nature of the other electrode with which it is connected. So single electrode has no use. So when this zinc electrode is connected to copper electrode, as I have seen in the earlier example. So zinc rod when connected to copper electrode, or zinc electrode when connected to copper electrode, oxidation occurs at zinc electrode, so reduction occurs at copper electrode. So only when zinc rod is connected to another electrode, either oxidation or reduction takes place. Okay, if same zinc rod is connected to sodium electrode, then sodium electrode acts as anode, zinc electrode acts as cathode. Why? I said the reduction potentials of the two electrodes will decide whether the particular electrode is an anode or cathode. The electrode whose reduction potential is higher, that electrode acts as cathode. The other electrode with lower reduction potential will act as anode. So if you consider zinc copper system, copper has got higher reduction potential, therefore it acts as cathode and zinc acts as anode. In the same way, if I take zinc sodium system, reduction potential of zinc is more than sodium, therefore zinc electrode acts as cathode, whereas sodium electrode acts as anode. So a particular electrode can act as an anode and cathode depending upon the other electrode with which it is connected or coupled. So such electrodes where they can behave as anode or cathode are called reversible electrodes. This you should remember because this term reversible electrode will be using when we discuss about reversible and irreversible cells. So any electrode which can act as an anode or cathode are termed as reversible electrodes. A pair of reversible electrodes will constitute a reversible cell. In the sense, the cell reaction can be reversed. We will understand that later. We will discuss it later. So here, electrode potential is defined as the tendency of the electrode to lose or gain the electrons. So if it loses the electrons, then the potential developed is called oxidation potential. So whenever oxidation takes place at an electrode, oxidation potential develops, and if reduction takes place at the electrode, reduction potential develops. Okay, so if it is zinc electrode, when zinc electrode is coupled with copper electrode, oxidation takes place at zinc electrode, so it assumes or possesses oxidation potential. When same zinc electrode is coupled with sodium electrode, it acts as cathode. So when zinc electrode is coupled with sodium electrode, reduction takes place at zinc electrode, the potential developed at zinc electrode will be reduction potential. So depending upon whether oxidation or reduction occurs at an electrode, oxidation and reduction potentials arise. Therefore, electrode potential is nothing but the tendency of the electrode to lose or gain the electrons is called electrode potential. And the oxidation and reduction potentials. An electrode, a reversible electrode possesses oxidation as well as reduction potentials. All the metal ion electrodes are reversible electrodes. In any metal ion electrodes, they are all reversible electrodes. Even hydrogen gas electrode is reversible electrode. Chlorine gas electrode is reversible electrode. Even calomel electrode is reversible electrode. Silver fluoride electrode is also reversible electrode. Right? We will be learning that. So, in all reversible electrodes, the electrodes will either attain oxidation potential or reduction potential depending upon the other electrode with which it is coupled. So when an electrode possesses both oxidation and reduction potentials, how are these oxidation and reduction potentials are related? So all reversible electrodes possess both oxidation and reduction potentials. So oxidation and reduction potentials are equal in magnitude and opposite in sign. I repeat, all reversible electrodes will possess oxidation and reduction potentials. So under given set of conditions, oxidation reduction potentials of an electrode, of a reversible electrode, are equal in magnitude and opposite in sign. What I see? So if we consider standard reduction potential of zinc electrode, it is minus 0.76 volts. It is the, according to IUPAC convention, we are supposed to use only reduction potentials. According to IUPAC convention, we are supposed to use only reduction potentials. Why? In order to avoid confusion. When I say electrode potential of X electrode is minus 0.5 volts, it goes without saying I'm talking about reduction potentials. So you should assume that when electrode potential is mentioned, it is only reduction potential, unless it is specifically mentioned as oxidation potential or reduction potentials and oxidation potentials, the way they are represented, also will tell us whether the potential mentioned is reduction or oxidation potentials. For example, this is the standard reduction potential of zinc electrode. So, how do you represent the reduction potential like this? Because reduction is a gaining of electrons. Metal ions are converted to metal. So, if you write like this potential is a standard reduction potential. Look here. So, if it is oxidation potential of zinc, we write like this. Zinc oxidation means what? The process of losing electrons. Zinc atoms are converted to zinc ions. So, zinc is undergoing oxidation. So, when we represent like this, it represents standard oxidation potential. So, standard oxidation potential of zinc this is minus. Standard reduction potential is minus 0.76 volts. Standard oxidation potential of zinc electrode is 0.76 volts. Look here. For any reversible electrode, there will be reduction and oxidation potentials. And reduction and oxidation potentials of a particular electrode are equal in magnitude and opposite in sign. And the reduction potential of zinc is minus, whereas oxidation potential of zinc is plus. So look, magnitude is the same, but sign is opposite. So for all the reversible electrodes, there would be oxidation and reduction potentials, which are equal in magnitude and opposite in sign. And why standard reduction potential of zinc has got negative sign, and on the other hand, standard electrode potential of copper has got a positive sign, and the standard reduction potential of copper is plus 0.34 volts. So what does this sign indicate? The standard reduction potential. I simply say standard electrode potential of zinc is minus 0.76 volts. Standard copper electrode potential is 0.34 volts. So why is that in standard potential of copper has got positive sign, and why is the standard potential of zinc has got negative sign? So this is sign convention. So the standard electrode potentials, as I said, single electrode serves no purpose. We cannot achieve anything using a single electrode. It's useless. Like 0. 0 without any integer on its left hand side has no value. Whenever put a non-zero digit, then only this 0 has a value. So 0 as such with no other digit on its left hand side has no meaning. It is 0. There is nothing. But when I put a non-zero digit on left hand side, the number becomes 10. So in the same way, a single electrode is of no use. It serves no purpose. We always require 2 electrodes to constitute a cell, and we want to, whatever purpose we want to use it, we use that for that purpose. So here, single electrode potentials. I cannot just determine electrode potential of zinc electrode by taking single zinc rod dipped in zinc sulfate. I cannot do anything. I cannot determine single electrode potentials. Therefore, the electrode potentials are determined using standard hydrogen gas electrode. We will be discussing about in the future session. So, all standard electrode potentials are determined using standard hydrogen electrode. I repeat, standard electrode potentials. Look at the value E naught. E naught represents standard electrode potential. With E naught cell, it is standard EMF of the cell. Okay. So standard electrode potentials are measured with respect to standard hydrogen electrode whose potential is taken as 0. Because it is impossible to determine an electrode potential without having another electrode whose potential is known. When no electrode potential is known, the problem is how to determine electrode potentials. Therefore, this problem is solved by taking a standard hydrogen electrode as a reference electrode. So, all the standard electrode potentials are measured using standard hydrogen gas electrode. And since the standard hydrogen gas electrode potential is not known, it is assumed to be 0. That's why it's called as a primary reference electrode. So standard hydrogen gas electrode is called primary reference electrode, and its potential is assumed to be 0. It's assumed to be 0 because in order to determine all other electrode potentials, this is taken as a reference electrode, and therefore its potential is fixed as 0, or it's assumed to be 0. That's all. So assuming this electrode potential to be 0, SH is connected to different electrodes, and EMF of the cell is determined from the EMF of the cell by subtracting the hydrogen gas electrode potential. Because standard hydrogen electrode potential is 0, EMF of the cell using SHE and any other electrode would be electrode potential of the other electrode. So if zinc electrode is connected to SHE, zinc rod dipped in 1 molar zinc sulfate solution at 25 degrees Celsius and connected to SHE, and EMF is determined, EMF turns out to be negative, means the electrode potential of zinc is minus 0.76 volts. Because EMF of cell is what? E cathode minus E anode. Cathode reduction potential minus anode reduction potential. So if one of the electrodes potential is 0, EMF of the cell would be equal to electrode potential of the other electrode. Okay. Since standard hydrogen electrode potential is taken as 0, whenever SHE is connected to any other electrode under standard conditions, EMF of that cell would be equal to standard potential of that electrode. Okay. Now, so standard potential of zinc and that of copper electrodes are determined with SHE. Standard potential of zinc has minus sign and standard potential of copper has got plus sign, which indicates that zinc electrode when connected to SHE acts as anode, and copper electrode when connected to SHE it acts as cathode. So any electrode whose standard potential is minus sign, it means that all those electrodes with the minus sign of their reduction potentials indicate that they act as anode when connected to SHE, and all those reduction potentials whose sign is plus means those electrodes when connected to SHE act as cathode. So here copper, standard electrode potential of copper is plus sign, standard electrode potential of silver is plus 0.80 volts, means again silver electrode when connected to SHE it acts as cathode. Similarly gold electrode, it acts as cathode when connected to SHE. If you take zinc electrode, aluminum electrode, magnesium electrode, sodium electrode, potassium electrode, all these have got negative reduction potentials, means these electrodes when connected to SHE act as anode. So that is the importance of sign of electrode potentials. So standard potentials of electrodes, if they are negative, those electrodes act as anode when connected to SHE. Standard reduction potentials, if have got positive sign, these electrodes when connected to SHE act as positive electrodes. Okay, then what is E cell and E naught cell? So E cell is EMF of the cell. EMF of the cell is equal to electrode reduction potential of cathode minus reduction potential of anode. Whenever we write E naught minus E cathode minus E anode, it goes without saying it is the reduction potential. So EMF of the cell is a reduction potential of cathode minus reduction potential of anode. If you take in terms of oxidation potentials, this is in terms of reduction potentials. If you take oxidation potential, what will be the equation? It will be E anode minus E cathode. Because we learned that reduction potential of the electrode is higher, that acts as cathode. Therefore, E cathode, reduction potential of cathode minus reduction potential of anode is E cell. Okay, EMF of the cell should be always positive, it cannot have negative value. EMF can be 0, but EMF cannot be negative. So also if you consider oxidation potentials, since oxidation reduction potentials are equal in magnitude and opposite in sign, In terms of oxidation potentials, EMF of the cell is E anode minus E cathode. And these electrode potentials, like E cell, we do have E electrode and E not electrode. This is the electrode potential, this is standard electrode potential. This is EMF of the cell, this is standard EMF of the cell. So when do we call the electrode potential or EMF of the cell as standard? When we measure these potentials or EMF are under standard conditions. What are standard conditions? Because electrode potential varies with the temperature and concentration of the electrolyte. So if you fix the concentration and fix the temperature, then electrode potential remains constant. So if concentration of the electrolyte is 1 molar, if temperature is 298 Kelvin, and if it is a gas electrode, pressure of the gas electrode should be 1 atmosphere. So when these conditions are fixed, concentration and temperature, and concentration of the gas depends upon pressure. If you fix the pressure, electrode pressure of the gas electrode also, electrode potential of the gas electrode also is fixed. So if you maintain concentration of the electrolyte as 1 molar and temperature as 298 Kelvin, then the electrode potential measured is called as a standard electrode potential. And if the same conditions are also maintained in the galvanic cell, both the electrodes are in contact with 1 molar electrolyte solutions at a temperature of 298 Kelvin, then EMF of that cell under these conditions of concentration temperature is called as a standard electromotive force. So this is the difference. E electrode is simply electrode potential, E not electrode is standard electrode potential. So also it is EMF of the cell, this is standard EMF of the cell. These two are variable. With change in temperature and concentration, these change. Whereas these are constant because you are fixing the concentration and you are fixing the temperature. So these are constants and these are variables. Right? So let me stop here. I will continue in the next session because the time is about 40 minutes. So regarding reversible and irreversible cells, let me discuss in the next class. Please comment in the comment box if I got any doubts. Thank you.